Hi, kids. All right. If you remember when we talked about work and energy, this unit was really the first unit where we really didn't introduce anything new. Although I guess we introduced springs, but as far as the motion, we didn't really introduce anything new. But doing things using work and energy was way, way, way easier. So this is a super duper important unit. There are definitely going to be questions about this on your AP test. So, first of all, just to understand that energy, if you look it up, it's defined as the ability to do work. Okay? In fact, if you look on your equation sheet, you will actually see it says this: change in energy equals work. So if you do positive work, that means your object is gaining energy. If you do negative work, that means your object or system is losing energy. The energy is being taken away. Okay? But energy is the ability to do work. If you look up what is work, okay, work is defined as force times distance. If you look on your equation sheet, this is actually how it's written on your equation sheet. It's written like this. Okay. What the reason they write it this way is, first of all, the College Board wants you to remember that and think about work as the change in energy first, and then think about it as force times distance. So if you are solving problems, you should be thinking, oh, how do I find work? Well, can I find the change in energy? That's how you should do it first. And then if you can't do it by doing change in energy, then you should be thinking, oh, force times distance. But remember, F and D, the reason they write it this way, F and D must be parallel. So F and D must be parallel, and F must be constant. When we have situations where F is not constant, like a spring, which we'll do in a little bit, then you can't use that equation. It doesn't work. Okay, sorry. So if you have, let's say you had a situation like this, you have a boy who's pulling a wagon up at an angle. So here's my applied force. And let's say that there is some friction acting on this. There's the force of gravity. There's the normal force. Okay. And the question was, hey, if your system is just the wagon, which forces are doing work, which forces are not doing work, and the forces that are doing work, are they doing positive work or negative work? So you would have to break this into its components. This would be like my perpendicular component. This would be my parallel component. So then FA parallel would be doing positive work. It would be adding energy to the wagon. The force of friction would be doing negative work. It would be taking energy away from the wagon. So if you push this thing along, and let's say later on it is moving faster, well, that means that FA parallel was winning. It was adding more energy than FF was taking away. If it's moving at a constant speed, we already know that means the net force is zero. But in terms of energy, that means, hey, whatever energy FA parallel is adding, FF is taking away the same amount. So it's not gaining or losing energy, so that it's moving at a constant speed. And then FA perpendicular, the normal force, and FG are doing no work. Why? Because F and D are not parallel. It's moving this way, and the forces aren't parallel. So there is that. Remember, you need to know this. Power is the rate work is done on your formula sheet. So a lot of times we think power is work over time, which it is. On your formula sheet, it's actually written like this. Again, why do they do it that way? Because the College Board wants you to think in terms of energy first. So power is the change in energy per time. Remember, units for energy are joules. And what were the, oh, sorry. So power is going to be joules per second, or what was that again? Oh, yeah, it was a watt. Okay, but yeah, that's that. Then we talked about the different types of energy. So let's say you have an object by itself. Well, if you have an object by itself, the only type of energy it can have is kinetic energy. And remember, kinetic energy stands for energy of movement. Okay. And the formula for it is K equals 1/2 mv squared. And, okay, that is on the formula sheet. I should mention energy is not a scalar. So, again, remember when we were talking about vectors, positive and negative just tells you direction. Well, that's not the case with a scalar. Positive work tells you something. It tells you you're adding energy to your system. Negative work means that you're taking energy away from your system. But kinetic energy is the energy of movement. So let's say you have, for example, I don't know, you have some problem where you have something that's coming down a ramp, some random object box that's starting from rest. My initial velocity is 0, and it's going down here, and it's going to be moving. Okay. Um, Remember, in physics, there's always essentially there's two pictures. There's an FBD, and then there's a picture like this where you'd say, well, I am going from this point to this point, and then I got to use my picture to write my equation. So let's say your system is the object only. Well, if my system is the object only, that means that the only type of energy I can have is kinetic. And here, I don't have any kinetic. Why? Because it's not moving. So then you would say, well, I have nothing there. And down here, well, if I was to draw my block, look, hey, look, it's moving. See, I did minor in art. So I have kinetic energy down here. Well, that means there was some outside force doing work on my system. And if you want to figure out what that outside force is, you could draw your FBD, or you could just use your brain. But in this case, that outside force, let's say that there is no friction here. So there's no friction, just to make it a little bit simpler. So that outside force is going to be really, it would be like this parallel component of gravity that's going to be doing work on my system. So I would have an equation that looks like this. So that gravity is adding energy to my system, so that even though I start with nothing, I end up with kinetic energy. Okay, there's that. But that's kind of complicated and kind of difficult. So what if we wanted to include this force? So then that means our system, we need to include the Earth as part of our system. Okay, so if we include the Earth as part of our system, that means now we can have potential energy. You can have the potential energy due to gravity. Remember, most of the time we say this is mgh. The way it's written on your formula sheet, it looks like this, though. And we'll talk about why. Okay, the reason the College Board writes it this way on your formula sheet is because, remember, as long as g is constant, okay, which it is near the surface of the Earth, that you can call whatever you want 0 height. So maybe for this problem, it would make sense, hey, I'm going to call this 0 height, okay? Then what happens is really this is my change in y, and the change in potential energy is really what's important. So remember, near the surface of the Earth, you, as long as g is constant, or that you get to call whatever you want 0, and then you can just do the change. So then if you were to solve this, this makes it way, way easier. So if you were to say, hey, I'm going from A to B, well, now at point A, I have potential energy. And at point B, I have kinetic energy. Well, if I draw my FBD, I would have my FG pointing down, and I would have my normal force pointing this way, and there's no friction. But does everybody see how my normal force is not going to do any work? Why? because it's not parallel. That's the definition of normal force. So that you would have just this. And then look how easy that is. That is so easy to solve. And then you could solve stuff, no problemo. So that would be if you have here. But what would happen if, let's say that there actually is friction in my system? So now, rather than saying this is 0, what if I say this is not 0? So if this is not 0, okay, well, if that's not 0, then if you're to just do the object Earth system, this is what it would look like. You would have UG, you would have K, but not all this UG gets converted to K. Some of it goes away so that there would be work done by friction, and this would be negative work. But remember, most of the time you want to write it this way first, which means you are taking energy away. Away from the system, which means the system has lost usable energy. Remember, usable energy is called mechanical energy. Mechanical energy is energy that is usable, meaning that you can use it to do work. If I just rub my hands together, well, that's not very clear, is it? But if you rub your hands together, that you're going to produce heat. Okay, well, that heat is not usable energy. So mechanical energy is typically all forms of potential plus your kinetic. Okay, that is going to be what your mechanical energy is. So in that case, the case that we were just talking about, my mechanical energy of the system, which was the object Earth, my mechanical energy would be decreasing because I start with more potential, I end up with less kinetic. Why? Because friction is taking energy out of my system. Well, what would happen if you included friction as part of your system? So we have, let's say we had the same basic thing again. So, where this is not 0, I'm starting from rest. This is my point A, this is my point B. Down here, my block is moving, okay? And I said my system is the object, surface, Earth. Well, if I include the surface, that means that friction is part of my system. So if I was to say, hey, I'm going to go from A to B, now I have potential energy, and at point B I have kinetic, plus I'm going to have some heat that's produced. And then it would look like that. But still, if you look, because I'm producing this heat, my mechanical energy would have decreased going from A to B because my usable energy went down. Really what we're talking about here, and hopefully you see this, is called conservation of energy. A super duper duper important concept, which just states the total energy for a system stays the same unless work is done to the system. And this honestly should be kind of like a duh statement. One, because you've taken physics and you've worked with this quite a bit. But two, because this is just saying, hey, you know what? If you don't do anything to your system, then your energy stays the same. It stays conserved. Okay? Unless if you do work to your system, then you're adding energy or you're taking energy away from your system. So that's conservation of energy. And then, well, what happens, we did have another type of energy, which was the spring potential. So we need to talk about springs. Okay, and if you remember, there's a couple things you need to remember with springs. So let's say I have a spring, and that's how long it is. And then let's say I hang a mass from it, and it stretches out, so it looks like this. And then it's at rest when it's like this. Well, I could measure this. That would be my displacement. And then if I drew my FBD, you could say, well, I have the force of the spring up, I have the force of gravity down. As long as it's at equilibrium, those two forces have to be the same. And then if you remember, we did a lab with this where you graphed it, where it was Fs and then X. It came out to be linear. The slope was equal to K. Remember, K is the spring constant, which is just a fancy way of saying how stiff is that spring. And then we ended up with this equation, F equals Kx. The way it's written on your formula sheet is like this. Remember, anytime you see these absolute values, that's the College Board way of saying, hey, this is a lovely equation to find the magnitude of the force. To find the direction, you are going to have to draw your FBD. Okay, so, but that was there. Remember, if you go back to our graph, if you find the area told us, which was, it's really 1/2 this times this. Well, that is going to be this times this is work, which is energy, which is change in energy. That was my potential energy stored by the spring, which is going to be 1/2 x times Fs, which is, if you do the math, if I put in k times x here, you get 1/2 kx squared, which is on your formula sheet. Okay, so now if you have a system that includes a spring, you now have a new type of energy, which is the elastic spring energy. But again, that's on your formula sheet. Just make sure you can locate it and find it. So like maybe we had a problem, something like this, where if we go back to our problem from before, so let's say you have something like this, and then maybe it runs into a wall and there's a spring there, so this goes down. This is not 0, and then it's going to hit the wall, so that I start from rest, and then I end with it compressed. I don't know, compressed. And then you'd say, hey, this is my point A, this is my point B, A to B. Well, what type of energy do we have? So let's say our system is the spring, object, Earth. We're not going to include friction as part of my system, so you'd have something that looks like this. I start with UG, and then in this case, if it compresses all the way and it stops, I just end with US. Okay, I could go right before if I wanted to, but I'm going to do that. And then, well, going from this point to this point, was there work done? Sure, there was work done by friction, and you would have something like this. But just remember, this would take energy out of my system, so my mechanical energy in this case would go down. Not all of this UG gets converted to US. But so that was springs. And then the last thing we talked about in this unit was universal potential energy. So universal UG. Okay? The formula for universal UG, if you look on your formula sheet, it's negative GMM over R. And you might be like, what the heck? Why is there a negative? But remember, the only time you can have UG is if you have FG, if you have a force of gravity. So that, near the Earth's surface, really we are talking about, remember, on the formula sheet, it's written like this. And then, again, this is on your formula sheet. Okay. Although on your formula sheet, they write M1 and M2. I'm going to write it this way just because, again, it's going to help us figure some stuff out. But near the Earth's surface, really what's important, you can call whatever you want 0 because it's the change that's important. Well, universally, you don't get to call whatever you want 0. The only place universally that UG equals 0 is when FG equals 0. So really, the only place that you truly have no potential energy is when you have no force of gravity. Well, when is that? If you remember, Fg equals g mm over r squared. Well, the only time this could be 0 is if your r right here is ridiculously big. So Fg equals 0 when r equals infinity, when it's just ridiculously big. Okay, so um, so and then why do you have a negative? Well, here's why you have the negative. So if you are an infinite distance away, that's where it's 0. If you're less than an infinite distance away, you are underneath 0, which means that's why it has to be negative. We demoed this with the spandex. So if you think about your spandex, here's my spandex, and remember we put something down here that represented maybe the Earth. This was where r equals infinity, which means this point is where Fg equals 0, which means Ug equals 0 here. Well, guess what? If we're down here someplace, do you see how I am under 0, which means it's negative? Okay. Hopefully that makes sense. And then what type of problems did we do with this? Most common problem was you have an escape speed problem. So let's say you wanted to escape the Earth in a rocket ship, and let's say your rocket ship is in orbit, and your rocket ship is going to be moving like this, and you want to escape the Earth. Well, if you want to escape the Earth, well, how do you do this first? You draw a picture. Well, here's my initial picture, and then here's my final picture. My rocket ship is over here, and where I am an infinite distance away. And really, if we're trying to find escape speed, then I'm not doing work on it. Just want to know how fast do I have to be moving here so I get to here. Well, as I go this way, just like as I'm rolling up, I'm slowing down so that at this point my speed is 0. So, hey, look, this is my point A, this is my point B. So what type of energy do I have here? Well, I have UG, okay? Why? Because I'm not an infinite distance away, and I have K. And then what type of energy do I have here? Well, I have no UG, and I have no K, so I have nothing. And then that's my equation. You might think, well, that doesn't make sense. No, it does, because negative GMM over R plus 1/2 mv squared equals 0. And again, do you see the nice way of doing big M, little m? My little m goes away, which means my mass of my rocket ship doesn't matter. And then you could solve for V, and then you could solve for the escape speed. But again, you're not going to memorize stuff. You're going to understand stuff. Another type of problem like this might be something like this. Hey, you know what? There's an astronaut hanging out on an asteroid. This astronaut is going to throw a ball straight up, and then the ball is going to escape moving so fast. So again, here's my point A, here's my point B, point A, point B. I have UG, I have K, and then at B I have a different K. And as long as I'm in outer space, there's no friction or anything. And then you could plug in stuff. Again, this would get plugged in here, this would get plugged in here, then you could solve for how fast you're moving there. All right, that was energy in about 25 minutes. Bye, kids.